Okay, so I got this problem from Quest. It says, during a baseball game, a batter hits a high pop-up. If the ball remains in the air for 6.66 seconds, how high above the point where it hits the bat does it rise? Assume when it hits the ground, it hits at exactly the level of the bat. The acceleration of gravity is 9.8 meters per second squared. Answer in units of meters. Okay, let's begin by highlighting what we know is important. So we know that the ball remains in the air for 6.66 seconds. We know the acceleration of gravity is 9.8 meters per second squared. And the question is that the question's asking us, what is the height it reaches? That's what it means. What is the height it reaches? And then this is important, which is assume this. If you play baseball, that kind of doesn't make sense. But in physics, we simplify everything because we can, and it makes the math a lot easier. So we're assuming that the ball was hit here, it went upward in this fashion, and then it landed here. In other words, pretend the batter hit the ball ground level. I know it doesn't make sense, but we're gonna do that. So here's the sketch. What we need to find is this, okay? This would be the height. So normally we would write our coordinate system. This would be the y-axis. To keep consistency, I'm going to copy this one. And then I'm going to rotate it 90 degrees. And you'll see why, okay? So the first step when you solve a physics problem is to draw a sketch, which I already did. Then we write down the given information, that is, whatever we know. Normally, well, the explicit given would be anything that has numbers and we can use. And then the implicit given is something or things we can figure out based on the sketch or the words. So we know that the time is 6.66 seconds. Don't trip about this number. If you know a little bit of philosophy and theology, you know that this number is not a bad number, so don't worry about it, okay? Then, if you want to know what this means, ask me during class. I'll tell you, based on the book of Revelation from the Bible. Next, we know that the acceleration of gravity, so A for acceleration, I'm going to add a little g here, is 9.8 meters per second squared. Just so you know, guys, this is a constant on planet Earth. And we don't write it like this, A sub g. It has its own symbol. Its symbol is just lowercase g. So next unit, or even for the lab, instead of writing, when you have the acceleration of gravity, instead of saying A sub g or just A, we would use the lowercase g. But for now, for this to make sense, based on the equations we derived in the previous video, I'm going to just ignore it for now, okay? And if you think about it, that's all we know. So we need to find the height. We can call it h. However, we don't have an equation that will give us h explicitly. And what we can do is this. That's why I have this here. Let's label what we know. This would be the initial position. I know you're saying, well, this is the initial position. However, if we move like this, it doesn't matter. The value doesn't change, right? Because what we know is this is like the x-axis. This would be the x-axis. This would be the y-axis. So the x-coordinate here is the same as the x-coordinate here. So what we're going to know is this will be initial x naught. And this would be x final, just x. We want to know this distance. This distance is what we call displacement, or delta x. That is what we want to know, delta x. And we know that delta x, well, there's many ways to find it, but we want to know delta x. The reason why I'm not using the original sketch is because normally you would call this delta y because this would be the y coordinate. But I've rotated this sketch 90 degrees so that this is the x-axis. And we do that in physics a lot. We rotate the coordinate system to make the math easier. Okay? All right. So now let's go back to the original sketch. This is the explicit given. This is more of a little bit of implicit. But there's one more thing we have to consider. We want to know what is the height that it reaches, the maximum point. So at this point, something happens with the ball, with the baseball. At this point, it goes like that. The ball stops, okay, for a brief moment of time. It stops. So we can say that at this point, the velocity would be 0 meters per second. That's a fact. Now you have two options. Because truly you only need information of the ball as it goes from bottom top or top bottom. It doesn't matter what you pick because this is symmetrical. The time taken to get to this point is going to be identical to the time taken to fall to the ground. Because your lab will have things falling, I'm going to take the top bottom approach. Meaning this is going to be my initial point and this is going to be my final point. That makes this velocity my initial velocity, because now I'm only concerned about the motion from here to here, just as if someone had dropped this baseball from here, okay? That means this is my final velocity, which in all truth, I don't really need. This is the one that I need. This is part of the implicit given. So we're going to say V naught 0 meters per second. Okay. Now we have everything we need to find displacement, or in this case, the height. We're going to use one of the equations we derived. In for physics problems, you'll have 3 variables and you need to find a 4th one. Or if the equation has only 3 variables, you're going to have 2 and you need to solve for a 3rd one. In this case, let's check. Delta x, we don't know. So that means we should have 3 more variables. Initial velocity, we do have it. It is 0. I know it is 0, but we have it. We know what it is. Time, we have it. Is this one? Well, not really, but barely, okay? And then acceleration, well, we have it. This one here. Now, we'll write the right equation for us to solve this problem. Delta h, which is going to be the height, delta x, which is the height. That's going to be initial velocity. Now for the time is the time it takes to go from the from the top to the bottom. So let's call this time bottom plus 1/2 the acceleration of gravity. That's what's causing the ball to fall down, times the time from top to bottom squared. How do we find the time to go from the top to the bottom? Well, that's simple. We said everything was symmetrical. So if this whole trajectory is 6.66 seconds, half of its trajectory will be half the time. So we can say T bottom is 3.33 seconds. Normally I would call this T prime or T1. I just wanted to show bottom to make it a bit more clear. Now let's plug in what we know. Let's plug in our given. Okay, notice what's going to happen here. 0 times 3.33 is 0. It cancels out. So then we can say this is out. When we plug in our numbers into decimals, all we got to worry about is this part. Be careful with that square, okay? And there we have it. Our height is 54.3356. 1, because it's height, that would be meters. Furthermore, they said answer in units of meters. So when I put this into decimals, I just type the number, because when they say answer in units of meters, it means anything you write in the box represents the meters. That's it.